Hello everybody, this course is part of the Compilation and Programming with this course at ENS de Lyon. And this course will be about functions, the syntax, semantics, and typing. So in this course, the global approach and the main objectives is to give a semantics to functions in an imperative setting with problem about dealing with variables and the scope. So the semantics you will see here is inspired by what I have found in the literature when reading and writing semantics about imperative programs. And I will show you different ways to deal with variables and different environment of executions you encounter when executing several functions. So the big challenge of this course is to deal with variables in an imperative settings and how to get back to simulate the operations you have in the stack in the execution of real function in a real system. We will show both big step and small step operational semantics here. And we will observe that things are a bit more complex, but also more constructive. It is, in a sense, closer to what you will specify in a compiler than with a functional calculus like lambda calculus that has no imperative aspects. To finish with this slide, this is a reminder of how I do with my courses in those videos. The course is on video, and as much as possible what is written in orange it's paper proofs that I do during the video, and what's advised is to interrupt the video to try to do a bit the proof, or at least understand how you would do the proof before reading the video, or other ways you could also, if you feel confident, do this way. If you feel a bit that it's a bit too difficult, you could, on the contrary, read the video and then interrupt the video and try to see if you would be able to do it again or to understand it by yourself by redoing the proof on paper. This course is made of two parts, and this first video contains the first part, which is probably the longer one, and it gives the operational semantics for functions. Before digging into the operational semantics, we must define a syntax for functions. So I don't know if you remember, but here is the syntax we had for mini-while language. It is not exactly our mini-while language, the mini-while language we have, because we extended it for functions. That's the second line of the statement that you can see here. So remember, we had the expressions that allows you to do arithmetic operations and variable access and all that kind of things. It didn't change, so you can have a look at the previous video on semantics to if you want to recall that, but it's not, you don't need too much about this here. The second statement, which is a new one, which is a simple function call. So one thing that is interesting to notice is that we don't have function calls as generic as you would have in C, for example, where you would be allowed to do f1 of 1 plus f1 of 2 as an expression itself, and have several called functions in the same statement. Here we would use statement to be assignment to one variable of a function call. It's a bit reductive compared to what you have in practice. In practice, you can still express exactly the same programs with a few more intermediate variables. And it's easier for us to define the semantics. So we consider it's a good compromise here. The other statements is the statements you already know. You have skip that does nothing. You have the sequence. You have test, and you have the loop. Same thing. They were detailed in a previous course. I won't necessarily have to detail this here. Before, that was mostly our syntax. When we were doing typing, we were adding a bit of variable declarations, but now we need variable declarations and function declarations. So the syntax for the program itself is much more complex than what we had before. I mean, there's much more cases. What is a program in your new language? It's made of three things. Program is def body. D is a set of variable declarations. And as you can see, the third line, D is for variable declarations. Those will be the global variables. Inside my program, then I have def, which is a set of function definitions that I will define below. And I have a body like you would have in C, the main body of the main method. So except that I don't call it main here, I just give one body. It's roughly the same principle, just it's easier for us in the semantics to identify it properly. What is a body now? A body is a statement, that was more or less what we had before, but it's also a set of variable declarations D, the variables locally defined for your statement S. What is variable declaration? It's a set of declarations, so that's why at the right you have a sequence of declaration. Each of them is of the form var x semicolon tau, which means I declare the variable x with the type tau. Tau would be typically int and boolean, but you can extend it with whatever type is interesting for you. Then, finally, we get to the definition of functions. A definition of function is something that looks like what you have in the first line of the function def statement here. The second line is simply the fact that you can define several functions inside this statement. What is a function definition? It is made of four parts, we could say. Tau here is a return type. I mean, I use a syntax as close as possible to a C-like syntax. To f x1 to 1 to n, which means I have a function f, so that's the name of the function, f. 2 is a return type, and to 1 to 2n is the types of the argument, and x1 to xn are the parameters. I mean, I don't introduce something strange here. Then you would have like to have the body of the function. Here, to simplify a bit our work, I don't know if you noticed, but there's no return statement inside the statements, whether when you have methods, you would like to have return statement. Here, to simplify our work, we say that the body doesn't contain return, and it finishes, if you want, by a specific statement, return of E, except that it's not inside the statement, so we know that it can only be at the end of the body. So it prevents you from putting a return at the middle of the body. So it's a bit restrictive for how you can express your programs. Of course, in practice, you can have the same programs as if the return was in the middle. You just do a conditional branch at some point to go to the return E statement. And the good point is that it will help us to define the semantics, because we won't have to deal with what should we do if the return that is at the middle typically, and what should we do if there's no return statement. So we know that there's a return statement and it's at the end. Compared to what you would imagine of a real-life language, function call is not a standard expression, but it's a special statement. It's that's what we had here on the second line. And return only appears at the end of the function definition, so we won't have to deal with return at the middle. So in this slide, I'll show you a few things we will use for dealing with variables in the rest of the course. I'll use the function vars of D. Remember, D is a set of but declarations of the form var x tau. So vars of D is a set of x used in the D declaration. So it's all the variables defined declared, I should say, in the declaration D. The good property with typing is that it ensures progress. That is, you can always evaluate something, which means you can always access a variable in particular. And we say that, oh, this was true, but on the condition that variables will be initialized at the beginning, because else accessing a variable x that has not been initialized will not result in anything in our semantics. So one of the solutions we have seen to ensure progress is that we could assign to all variables of D a predefined value, which is 0 for integers and true for Boolean, for example. So I don't know if you remember, but in the previous course, we were able to update the store sigma by saying, oh, now I update the value of X to be the value V. So this was a new store that could simply be same as the store sigma, except for X that was the value V. So we will need something a bit similar, but a bit extended. That's why I called it a global store date. We want to define exactly the same kind of things, but mixing of stores themselves. So sigma prime big X to sigma means this is a store sigma prime where all the variables in the set big X of variables, so this is X, Y, and Z, for example, are given the values that are inside sigma. So said other way, a bit more formally and perhaps a bit easier to read, sigma prime of X to sigma of X is either when if the small x is in big X, I take sigma, and if the small x is not in big X, then I take sigma prime. So this will allow me to hide part of the store sigma to give them a special value. Before getting into the semantics, I define a few functions here, a few helper functions for my semantics. For each function f with name f, I'll use three different functions, but functions in the same function that I can use in semantics, so in sense, mathematical functions, not functions of my program. Those three functions are params, weight, and body, and params of f will give me the list of parameter variables. So if the first formal parameter is called x, x will be the first element of the list. So it's ordered, of course, as ordered in the call or in the declaration of the function. So if you come back to the syntax, params of f for this f here gives me x, x1, etc. to xn. Second function I will use is weight of f, which is the expression in the return statement. So in that case here, it's the small e here. And finally, body of f is the function body, what is at the center of the declaration. So I suppose that those are global functions that are known everywhere and that are defined everywhere, and I can use anywhere in my semantics without explicitly stating where they are picked, where this information is picked. If you wanted a more constructive way to do that, you would define a context like the big phi here that would hold those informations, basically those three functions, as under the form probably of three mappings from function names to informations, or one mapping to from function name to informations. And you would populate this mapping at the beginning when starting evaluating the program by storing the information you need and exploring the syntax adequately. It's very simple to define that, but it would take us a bit of time and it's not particularly interesting, so I won't do it here. I will just suppose that I know those three functions. Before jumping into the semantics of functions, I'll just recall the big step semantics. So I'll try to spend not too much time, but a bit of time to be sure that we all recall what is the previous semantics, and there's no doubt about that. So this is a big step. So remember, the big step semantics is something that evaluates a whole program in one step. So it uses several steps, of course, to do it, but a big step semantics take a statement, which can be as complex as you want, an initial state, and produce a resulting state that is the state which is reached by evaluating the whole statement. Even if it contains loops or anything, it will just do everything in one big step. So remember, you had this evaluation for plenty of things. For example, assignment here, if you want to assign to X the expression E inside the state sigma, you produce a new state sigma. So remember, sigma is a store that maps variables to their value. So now I know, the new value of X should be E. So that's what I'm doing. I produce a new store here with X now maps to E. Well, in fact, to the evaluation of the expression E, because E might be 1 plus Y, for example, inside the store sigma. Val is a function that we defined before, and basically evaluate the expressions using the variables that can be given values inside the store sigma. So in this case, if it was 1 y sorry, plus 1, this would evaluate the expression E inside sigma that would probably map y to something, like, for example, to 2. And this would be 2 plus 1, so it will now map x to 3. So that's the assignment. Another important thing to understand is the sequence, also because it expresses what is the big step. How can we evaluate a whole program inside one single big step? Well, it's very simple. To evaluate a sequence of two statements S1 and S2 inside the store sigma, you do by step. You first evaluate sigma 1 to S1 sigma to sigma prime. Then this gives you a sigma prime. Then you evaluate the statement x2. So this is here. First you do that. Then you evaluate the statement s2 inside the store sigma prime and obtain sigma second. And finally, this is sigma second that is the result of your whole computation. So here we use classical notations for semantics, and this says if I know that S1 sigma reduces to sigma prime and S2 sigma prime reduces to sigma second, then this is an implication. I have the thing below. Also recall that we defined the evaluation of a whole program. So this was for statement, and we can sometimes say I want to. And what's new here is that now we will want to evaluate programs. So this is a bit the new part. And the new evaluation of program is state that if a program is this, which is exactly the syntax we've defined before, that is global variable here, function definitions, and main and variables of the main. Then to evaluate it, I take the statements that are here and I put them in an empty store and it produces me something. And that's what I will be trying to define now. And so here we are for the first semantics of function in a big step semantics. The first solution takes the idea that we don't care how much store manipulation we do. So it's probably the simplest solution from a number of equations point of view, but it is also probably the less realistic and it's faithful to what happened in reality, like in a compiler or at runtime. So what this rule does is that it first takes the body of the function f. So remember, body is a generally declared function that gives you the body. So it's a set of variable declarations and a statement that can be a list of statements, in fact, thanks to the sequence. In all the rules I will present in the following, I will use some generally defined functions bind. So bind is a primitive that creates an execution environment corresponding to the function. So here we have a bind one because we have several in the rest of the course. This first one will take the name of the function, a set of expressions, and a store. And it produces a statement and a new store. It will be defined below, but basically it's this bind primitive is a function that takes whatever is needed and produces the setting in which the function should be executed. So now that you have the statement and the store, you can evaluate the statement by a big step semantic, and you obtain a store sigma second. Remember that the evaluation of the big step semantic takes a statement and the store and produces a resulting store. So now that we've evaluated, in fact, the body of the function, we will see that the bind function gives us the body in the right setting. So now that we've evaluated the body, remember that return statement is outside the body. Can come back to this. Here, you see the return is outside the body. So we evaluate now the return statement, which is given to us by weight of f, in this newly produced store and gives us a value. Basically, it's the evaluation of what is inside the return, and this is the return value. What I could have explored before, but I've put it aside, is that I suppose the function cause was of the form x becomes equal to f of e1 en. So we see already that the bind function takes as parameters the expression that is given as parameter of the function. And sigma, which was a store before, and now it produces the new store sigma second, but with quite a few changes. And what are those changes? And this is the central part of this solution. Remember that we've just seen just before here a magical store update operator that just takes a set of variables and updates the store with a new partial store for some variables. And we will use that exactly. And this is why sigma second is a store after the evaluation of the body of f. So it's perfectly fine, except that it modified values for df and the parameters. And you have two cases that are possible. Either the variables inside the local variables of the functions, in fact, vars of df, or the name of the parameters of f, were not used in sigma. In which case, there's no point in having them now, so we should just discard them and having them to a known value, a void value if you prefer. The big problem is that I might have the same variables in df and inside sigma, that is in the global variables, for example, or in the variables of the calling function. In which case, what I did here, erased the previous value, and because of the scope of variables, because variables that are local to the functions does not exist in the global function, and the caller functions exist but have a defined value rather. Because of that, I should be able to restore that. So that's what this magical operator does here. It says, for whatever variables that are local to f, or that are parameters of f, I restore the previous value. I take it from sigma here. And the last thing you want to do is you want to update x with the return value, and I've just calculated the return value, so x is now v. So as the rule is a bit complex, I'll explain it a second time. So this rule applies when I encounter a statement that says call to function f and assign it to x. First thing I would do is that I would call the bind general function to provide me a statement that corresponds to the body of the function to be evaluated, and in a certain store sigma prime that initializes all the necessary variables. And bind needs the name of the function and the set of expressions that was given as actual parameters and the initial store. I evaluate this body, in fact, in this new store, and this produces me a new store sigma second. Finally, I just remember the value v that is returned by the function. That is, I evaluated the return statement of the function in a new store sigma second. And that's almost everything, except that I want to know what's on the right part of my evaluation now here. And it must be a store, because that's the signature of the big step semantics. And this store is exactly the store that is at the exit of the function, except that I must forget the local variables of the function. So I must basically just remember the global variables. So for all the variables that were local to the function, that is those inside df and the list of parameters, I should just forget the value. So that's what I do here. I restore the value inside sigma for those variables. That's almost everything, except that I must have an effect from this function, except the global variables updates, and the effect is assigning the value. So this is v, and I put it into x. That I've put aside what bind does. What bind does is that it creates a statement for the body of the function. So suppose it takes a function. So suppose the body of the function is div f sf, like above, here. And what the statement to return is simple. It's sf. The smart part is inside sigma. And in fact, sigma is the store as it was called, but I must initialize the parameters. And when I do to initialize the parameters, I assign to each of the formal parameter the evaluation of the expression that was given as actual parameter. If the parameters of f are x1 to xn, and the evaluation of ei is vi, then I assign x1, xn to vi, vn. Basically, I evaluate each of the expressions in the store sigma. It gives me vi, and assign it to each of the variables. The val function has been defined during the first course on semantics of expressions. So if you want to interrupt and have a look at how it looked like at this point in time, you can interrupt now the video. So a few notes on this semantics before going to an example. It's a call by value because we evaluate the expression before calling the function. And it evaluates each of the arguments, and parameters are directly put in the stores as initialization of variables. So what I suggest now is to try to evaluate the following program. The way I suggest to do it is that you try to do it by yourself, trying to apply the previous rule, and then you have a look at the way I do it. It's a simple program that has one function and one main methods, but it has a bit of overlap of variable names just to see how things overlap or are stored at which point in time. I guess at least some of you have done that they try to apply the semantics on the program, and what perhaps you will have asked me, or at least you would have wondered by yourself, is how do we start? Basically, we were starting with something on the form statement as a store sigma, and the store in fact was an empty store because at the beginning you don't know nothing about the variables. Except if you want to initialize the variables, that's something we've discussed during typing. But suppose we just start from an empty environment. Problem is that here we have a program. What I suppose is that at the same time you have the slides on the side, so you can check what a program is, and you know it's not on the form as. It's a bit more complicated. But as usual, what you do is that you would like to just evaluate the main function. So that's what we will do. We'll say, oh, S is the body of the main function. So I will exactly do this here and say, okay, no, I want to evaluate x is 0 followed by y is 0 followed by y equals f of 3 in an empty store, and this is a big step. Okay. So I don't know what will happen live if you will ask me and I will tell you to do it this way, or if you figure out by yourself or whatever. So now to evaluate this, I should first apply the rule for the sequence, and I will consider that this is a sequence. So this is an S. If you look at the rule for sequence, so same thing, you should have on one side the rules for the normal mini-while semantics. So here you will have a sequence with this on the left and this on the right. So if you check the rule for sequence, I let you do that, and you will see that you first evaluate the first part. So at least that's one of the premises. One of the premises say, okay, I have x0 in a store sigma, but here it's empty, and it reduces big step to a new store. Here I know the new store. The new store is x is mapped to 0. If you look carefully at the rule, it's the store empty modified by x becomes valuation of the expression e, which is 0 here, in a store which is the empty store here. So you will see that here indeed it is the new store is x is mapped to 0. Fine, and the other part of the sequence is the S2 statement, the other statement, and this second statement is itself a sequence. So I want to evaluate this big step. And I apply again the rule for sequence. I don't think I need to explain again the part on the left because it's the assignments y to 0. So this was done by the rule for the assignment. And I'll do the same, the rule for the assignment for y. And here it will just give me, so I start from y 0 in store sigma, which is x is mapped to 0. And I become sigma modified by y is assigned to 0. So overall, if I evaluate everything, it gives me x now is 0, y is now 0 too. Okay, and now the other part, which is the interesting part, in fact, but it was good to recover the previous applications on the semantics just to rehearse for you. And so now I just have one statement to evaluate, which is the function call. In a store, I will call sigma prime this. This should be a reduced big step to something. And here I apply the new rule for the call. So I put a small c here just for you to remember that it's a call, or I'll write here. And it's the rule we had on the previous slides if you're just seeing the slides of the course, so the slide just before the example. It has several premises. I'll write them from bottom to top because it's simpler. So here I want to first statement say, oh, I should check at body of f, and let's say it's df sf. Okay, so that I know. If you look at the example, the definition is a definition for y, and the statement is the three lines inside the body, the two lines inside the body of the method, which assign x and y. I'll just remove it here because as you won't follow anything, there's too many things here. So now we try to see what bind one is, and bind one of f and of the expressions that are in the call. So here it's just 3. And it just should provide me a s and a sigma prime. If you look at the definition of bind, you see that the s is in fact sf. So I use the same so that it makes one less symbol. I already have a sigma prime. I'll call this sigma 2. And what is sigma 2? So now you should have a look at the how is sigma defined in the bind function. And it's simply the sigma that I had before, so it's sigma prime, but with an assignment corresponding to the parameter. So here the parameter is named x, and it's mapped to 3 because 3 is passed to the function. So if you have a look, it's on the last lines of the slide 9 of the course. And sigma prime is this, so it gives me the statement, the store, so this is sigma 2, it is x is 3, y is still 0. So it was the second thing. The third thing you do is you evaluate sf, which is the body of the functions. So you want to have that, I'll still write sf in the store sigma 2 should reduce to something. So if you like look at sf, remember it is x is 1, y becomes 2, semicolon. It's easy to see that the evaluation of this is it's a sequence. So here we use a sequence, and it's very similar to before. So I will omit this here, and I'll obtain the new store x is mapped to 1, y is mapped to 2. One last statement of the of the call, the rule for calling a function says, oh, now v is the valuation of the expression e, which is, if you have a look at my function, it's x plus 1. In the store, I will call this sigma 3. This is x1 in sigma 3. Okay, this, if you have a look at the conclusion of the inference rule for the big step semantics, it gives sigma 4 that is defined as follows. Sigma 4 is sigma 4 is the sigma that you have at the end, which is sigma 2, no, sigma 3, but x and y were the parameters, so, and the local variables of the function, so they should be forgotten. So for x and y, I give them the previous value they'd have, which is the value they had in the in sigma prime, which is 0 in fact. But I also should update the y as here, and now y is mapped to the value v. I didn't evaluate v here. X was 3. No, sorry, x was 1, so 1 plus 1 is 2. So sigma 4 at the end is x is mapped to 0 and y is mapped to 2. It should be reported here and here. Here we are. So we did this reduction. So you can observe how variables were recovered at the end of the execution of the function when we computed sigma 4 here, and how they are assigned at the entry of the function inside sigma 2 here. I want to come back on one of the problems we have with this semantics. The problem is the part of the evaluation that does that. It restores part of the store as it was before the invocation. This is really impractical. So not to write the semantics, it's quite easy to write these equations and to understand what it does. I mean, not that difficult. But if you want to implement this semantics, it's very difficult to compute. You need to remember the set of those variables and the store that was existing before. In theory, the whole store. In practice, you could just remember the part of the store that will be erased. But still, it's not really, that's not how you want to implement this. It's not very constructive. It's really far from any implementation, no compilation of function. You never did something like that. So that's why we'll show another semantics.